Can you see this?
Yes.
Okay, great.
Are you at risk? Stroke classification created by the frenzied physicist. Our dataset from Kaggle consisted of health symptoms and traits of patients, as well as if the patient had a stroke or not, which was exciting because there were various possibilities of what we could do. Although there were some issues with the data that we needed to clean up, including imbalanced data, which we fixed by resampling, null values or NaN values, which we dropped, using getDummies to convert categorical data, which has strings, to numerical data, and dropping some columns as well. So why is predicting strokes important? Every 40 seconds, someone in the US has a stroke, and every 3.5 minutes, someone dies of a stroke. Every year, more than 795,000 people in the US have a stroke, and it's estimated that 140,000 Americans die of a stroke each year. We believe that being able to predict whether one is at risk of a stroke using our program could prevent potential strokes and even deaths. So why machine learning? Machine learning is important in this project because we can use ML to classify a stroke. ML is also going to a ton of separate fields, and it's not just computer science. As well, because human error occurs, ML is good because machines are more consistent and make less mistakes. ML can be used to effectively double-check diagnoses and even diagnose people with a stroke. Our website will provide users with the risk of having a stroke based on underlying health conditions or traits the users provide. So let's check out our website.
To summarize our data, we use histograms. Our first histogram shows us the people who have never experienced a stroke and the people who have, where 0% of the people who have not gotten a stroke and 100% of the people who have gotten a stroke. It shows that 587 people have never experienced a stroke, while 470 have. Our second histogram shows the average glucose level, where red represents the people who have had a stroke and blue represents the histogram tells you that people suffer to have a higher. Our third histogram shows the age, where red represents people who have experienced a stroke and blue represents people who have not. As you can see, people who have suffered a stroke are around the age 75 through 79. Our last histogram shows that people who have suffered a stroke usually have a higher BMI, which is body mass index.
The next type of visualization that we covered were scatter plots. I personally like scatter plots because they're lots of fun. You get to see trend lines, get some indirect inferences from them, and most importantly, you get to see where all your outliers are. So it really gives you like the bigger picture. So our first scatter plot was glucose, average glucose level versus age. So from here, like I said, indirectly, you can infer that when, just note, blue is people who've had strokes, red is people who haven't had strokes. You can see that all of our blue dots are towards the top. So that's like our older group. But when we're looking at average glucose level going from left to right, we can see that people who haven't had strokes, they tend to be more concentrated towards the left side of the screen. But then our stroke victims, it's like kind of flatter and longer, and it's stretching out into the right side of the screen. So there's kind of a soft inference from that. And then the next two scatter plots we have more or less cover the same topics. This is age versus BMI, and the next one is body mass index versus glucose. So if we're looking at, let's say, the third one, the average glucose level, we can see again is kind of correlated with stroke victims. They tend to have higher average glucose levels. But yeah, a lot of the times, or what we saw with these scatter plots is that the correlations between some of these features aren't really there, but it's still interesting to look at nonetheless.
The final scatter plot shows the correlation between age, BMI, and average glucose level. You can see that there isn't much correlation between age and BMI, but as the plots get bigger and closer to yellow, that means they have a higher average glucose level, which shows you that as you get older, you tend to have a higher average glucose level. The box plot shows the average glucose level for people who have a stroke, and it shows that commonly people who have a stroke tend to have a higher average glucose level. However, there are some outliers with a high average glucose level who haven't had a stroke. The heat map shows the correlation between our variables, and as the color gets closer to a yellow, that means they have a higher correlation. So for instance, stroke and age have a high correlation as it is a orangish color, whereas never married and age have a low correlation as it is closer to a deep purple.
Suhas, can you talk or no? Okay, I'll just talk for him. He was having Wi-Fi problems. So for our machine learning models, we just tried a bunch of different machine learning models. So we did a 80-20 split with our data, 80% being our training and 20% being our testing. Then we also did a stratified split so that we're equally sampling both classes evenly. We also did some, to handle our imbalance data, we did some resampling. So for our first two machine learning models, we did a decision tree and a random forest, which are very similar to one another. And so for the decision tree, I won't go too much into the detail because we've already kind of talked about it a little bit, but this is kind of like a simple decision tree that we made. It has a max depth of like 4. So you can see that like the colors kind of represent the classes. So the blue is the stroke class and the orange is the not stroke class. And you can see that when it's darker, that means that it's separated the classes better. And then when it's a bit lighter, that means that it hasn't separated the classes that well. And you can see as it goes down, it gets much, much darker. So you can kind of follow along through the site and kind of like test out like, oh, am I likely to have a stroke or not with this like simple example. And then we also applied grid search to this model and a few other models as well, just to tune our hyperparameters and to improve the scores of the different models. So we applied that to random forest as well. And the random forest, again, is basically taking a bunch of trees and training them on subsets of features and then letting them kind of vote. And the majority that for whichever class wins, and that's kind of like the final class.
One of the other models that we did was logistic regression. Logistic regression basically is a probability model. So you're going to get some sort of prediction, and that prediction is going to be between the values of 0 and 1. So if we look at our visualization here, up top, there's like a flat curve, and towards the bottom, there's like a flat curve. In the middle, it's kind of like going up. So those are our like peaks or like minimum and maximum. And then how we're going to get our point along that curve is we're going to add up all of our features together, and it kind of creates like a sum. And then from that sum, we'll be able to plot and get what our prediction is. Also, I'd like to add that this model did the best for us. It was like actually very surprising for us, but I'm going to let someone else explain that in a bit because we have a lot to say about that.
The next model that we used was the support vector classifier, which from the example, you can kind of see that it puts the data onto a hyperplane and separates our stroke and non-stroke groups with a boundary line. And for the grid search, we applied the RBF kernel, gamma, and C for our parameters. For the K nearest neighbor model learning machine, the model can be used for unsupervised learning, but in this case, we used it for supervised learning. It has a distance-based approach. It's kind of similar to humans where we choose our friends and groups based off of who is more similar to us. So you can kind of look at it in that sense, where the KNN looks at features and finds out what neighbors the data point is closest to.
Looking at our results, you can see that the logistic regression did best in all of our metrics, including accuracy, precision, recall, and F1 score, whereas the SVC did worse in all of those.
For the SVC, it came out with a lot of false positives, which basically means that the machine predicted a stroke when it didn't have a stroke, which is better for our data set because it's better to predict a false stroke than to predict no stroke at all. For the KNN, it did better than the SVC in all metrics except for recall, and even then the SVC was only higher by 0.01%.
I guess I'll take this again because my group member got kicked out of the Zoom because of the Wi-Fi. But so then for the random forest and the decision tree did a lot better than the random forest. As you can see that this is that both the accuracy and the F1 score are really high. And we think that this is because the random forest is training on subsets of the features that because we have like so few features that it's actually detracting from the model. So that's why the decision tree with all the different features performs better.
We performed a grid search, and a grid search is an algorithm for finding the optimal hyperparameters of a model to find the most accurate prediction. We performed a grid search on the random forest and decision tree model, and they were still all performed by the logistic regression. Performing a grid search actually wasn't a decision tree, which might be due to the lack of scope for hyperparameters or decision tree contained. The random forest had a better grid search result than the decision tree in accuracy, recall, and F1 score.
And that's pretty much our presentation. I just want to say I'm really proud of the frenzied physicists for the work they've done, and I'm sure all the TSIs feel this too. But it's very rewarding for us watching you all grow. And great job, guys.